Marginal cost is what people in the world of business, how they refer to the derivative.
Oh.
So it's really when it's the marginal cost when there are 100 washing machines produced, is they would read this as C prime of X. So they, we differentiate like we always do, 100 minus 0.2X. When you evaluate this at 100, you're going to get 100 minus 0.2 times 100. So that's going to be 100 minus 20 is going to be 80. Now, here's where the interpretation for, in the world of business, is a little different than in the world of math. So this is presented so you can understand that, but don't use this interpretation like on an AP exam question, because that is not going to lead to a correct mathematical interpretation. Because in math, what we're saying is that the instantaneous rate of change of cost at 100 machines produced is 80. So it's going to cost $80 more at that moment. Well, in math, functions are like continuous. But in the world of business, you know, they're not going to say there's anything of meaning between 100 and 101. Because it's kind of a discrete world that they live in rather than a continuous world. So their interpretation of this would be, you know, we would say the instantaneous rate of change of cost is $80 per washing machine when at that moment when that 100th machine is produced. They're going to say, their interpretation is going to be the cost of manufacturing the 101st machine is $80. So do you see how there's a slight difference really in what that means? You know, in math, it's a continuous. It may be $80 per machine at that moment, but by the time you moved, you know, a fraction beyond the 100, it may be something different. Well, that doesn't make sense in a world of business. So they're just going to call it, marginal cost, they're going to say, is the cost of making the next machine, which in this case would be the 101st machine.
Is that a distinction we need to know for the AP test? Or
I would say don't know. I would say this is, you know, if you end up doing something in the careers, you know, business, economics,
and
whatever.
also, if we end up doing something in the careers of business, I don't know if you know this, but is the notation going to stay the same?
Yeah, it's still the same. Yeah. So it's just how they kind of frame it in their world. Does that make sense? Other questions? So marginal cost, marginal anything really just means derivative. But they will describe it when they say, what does that mean in a business context? You know, they're going to frame it in terms of the next whatever it is we were talking about. Macy?
Number 29.
29?
Can we do 33 for P?
33.
It says describe the motion of the body, and the answer's confusing.
Okay, what page are you on there?
147. It's like in between 146 and 147 on both pages.
Okay. So let's see. Did we talk about the derivative of jerk being snap, crackle, pop in here?
Oh.
It was briefly mentioned.
Yeah. I just found that out a few weeks ago. I was like, oh, that is so cool. I knew that. So on 33, they gave us 2 minus 2 sine t, is that right?
Mm-hmm.
So S is 2 minus 2 sine t. And you didn't understand their description of the motion?
Yeah.
So yeah, and it's not always clear what exactly is meant by that. Can they give us a time interval? So they're not restricting what our time is, so I guess we're assuming this is going to go on and on and on forever. So we know that you found that S prime of t is going to be a negative 2 cosine t, and that S double prime of t, I don't know if this is going to help us much. It's going to be 2 sine t. So, yeah, it is kind of vague and open-ended about what they mean by describe its motion.
But they said that it oscillates between 0 and 4, and I didn't think there was an oscillation.
Well, so it's how you're thinking of this. They describe a simple harmonic motion. So what they're saying here, they're saying this particle is moving only in a line. So you might think of it as like moving up and down. So this, as we graph this sine curve, that's a negative sine curve. So it's going to do something like this. But what we're looking at here is time versus height. But if we were looking at this object, straight on, what's happening, you can't see time unless you stretch it out here. We're talking about something that's going to be going, up and down, and up and down, and up and down. And we're assuming here that there's no like air resistance, so it's just going to keep doing this forever. So that's the oscillation that you're seeing.
Is there a reason why your sine curve is graphed like above the x-axis?
Because of the translation 2 above there.
Oh, okay.
So it's going to have, it's going to be a translation 2 up and a magnitude of 2. So this would be like a low point of 2 and a high point of 4 there. And so, so it's kind of weird to think of it because we do this a lot, I think, in algebra 2 without clarifying that. We're saying this is time. Well, you don't usually see time, kind of like looking, across. But that's what's happening. This is its height, but it's just doing this. And so it's oscillating up and down as it goes, as it does that. Is that the part that was bothering you, the oscillation part?
Yeah.
Anything else?
I think the rest is probably fine.
Yeah. Okay.
They did it in a way that was confusing.
Uh-huh.
I don't think they needed to do that confusing.
Yeah, and it's kind of neat sometimes. We'll get to some more of these kind of particle motion things. And sometimes what's nice is we can now graph these parametrically because we can do x of t and y of t. So these kind of things that before were kind of hard to kind of describe or wrap your head around when you're only talking 2 dimensions, we can do better with parametrics because we can do things like, we can make like x the t variable time and see what its position is, and you can kind of see time going back and forth. So if an object is on a horizontal line, for example, and it does goes back and forth here, well, it's hard to kind of see what it's doing. But if you put time and then you get its position going vertically, you can see it kind of do something like that, where you can see, oh, it was moving in this direction for a while, and then you can see its change in direction, and then it changed direction again, which seeing it graphed that way is maybe a little easier to follow and make sense of than if it's just doing something like that. So there's a few more things we'll be able to kind of describe motion in once we get to parametrics. And then we can talk also more about these. We're going to see velocity and acceleration as vectors rather than just numbers, like when it's just moving in a line. We'll move things around in our flames. So it'll be kind of interesting. Other questions?
On homework 30, number 49, which is x equals t squared plus t.
X equals t squared plus t.
And y equals sine t.
Y equals sine t?
Yeah. And then the question is to find d dx of dy dx.
D dx of dy dx.
Yeah.
Oh, yeah. See, we're not really ready to talk about this. So,
Oh.
okay, but they're going to force us to kind of explore this a little bit. So there's a couple ways of doing it. Here's the way that this is not intuitive. So the first derivative, I think, of parametrics is fairly intuitive. Because what we get is that, we can take dx dt and dy dt because they're both functions of time. And so dy dx is going to be dy dt over dx dt, which if you think of it algebraically, I think kind of makes sense because, if you just said divide by this, that would be like multiplying by the reciprocal. So you could see these would cancel, and that's really equal to dy dx. And then this is how we're actually going to do it. Okay, so here's the way I like to think of this. So you can find, let's do this. So we know dy dt and dx dt. Dy dt is the derivative of sine t and that's going to be just cosine of t. And dx dt is going to be 2t plus 1. So this is our dy dx. Now the way I like to think of this is to take the derivative of this. So this is the second derivative of y with respect to x twice is another way of writing that. So what I like to do is think of it as doing, we said this is how we find dy dx, and I would do it as dy prime of dt over dx dt is how we're going to get the second derivative of x.
Why isn't it dx prime?
Well, there's a couple ways. So one way is to think of it as we're just going to, so we said that dy dx is dy dt over dx dt, as we just said. So now let's just say, here's our new function dy dx. Now to differentiate this function, we're going to treat it just like we did with y here. We're going to take its derivative with respect to t over, well, it's still over dx dt.
Okay.
Does that make sense? You could also do it as a chain rule. And I got to think, because I don't do it this way very much. And I'm afraid I'm going to say it wrong if I do. So we could say, I don't know. I better not try this without looking it over first. This way I know, because this is how I do it. So then the way I would think of this is we're going to take the derivative of y prime. Yes. So I want to take the derivative of dy dx. So I want to do this, dy prime dt over dx dt. So here now is it's like we're renaming this our new function. This is our y prime function. So we're going to take now, the derivative of this is going to be the derivative of that. And so that means we're going to take the derivative of the y prime function with respect to t. But we're going to divide it by that same dx dt that we got from taking that derivative, 2t plus 1. Okay? So this derivative, well, that's going to have to be a quotient rule. So we're going to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared over dx dt, which was the 2t plus 1. Okay? Ted, we okay there?
Yeah, I think so.
Okay. So then, what do we get? Nothing we want to do. So it looks like a negative 2t sine t minus another sine t minus a 2 cosine t. And then that's over the 2t plus 1 squared. And to divide by this is to multiply by its reciprocal, which is going to give us a cube down there. And I don't think there's much of anything we can do with that, is there? I don't think anything cancels or factors or anything.
Thank you.
Yeah. So give us a preview of this later, and we'll talk about it in more depth down the road too. But this is part of the calculus. Well, it'll be a long time down the road. But. Question? Does that help at all? That's how I think of it. There is another way of doing it too, but I have to refresh my memory. I'm afraid if I try to tackle that without looking at it, I'll end up spinning it wrong there. Okay, anything else? All right, well, in our part of our Blitz review, what we'll do today in 18 minutes is implicit differentiation and derivatives of the inverse trig functions and a derivative of an inverse function. Might have time enough to spare there and be able to catch up. So 3.7 is implicit differentiation. So what we mean by this is a function written explicitly is when you have y by itself and blah, 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 all the x stuff. An implicit function is when they're like hopelessly intertwined and mixed up and you can't, or it's just too difficult to try to separate off the y. So you go, well, we'll just understand that y is a function of x and go on and differentiate anyway and then use the appropriate derivative rules. So let's do that with something that has a little bit of challenge to it. So let's do e to the xy is equal to e to the, say, 3x minus, let's say, e to the x plus y. That's got a little bit of something for everybody there. Okay, you do that, and you work on that, and we'll go on. So here we're going to take e to the u du, right, our chain rule. So am I going, are we ready for this? So we're going to get the same exponential back, now times the derivative of x times y, which is a product rule. So that's going to be the first x times the derivative of y. Well, we don't know explicitly what y is, so we'll just call it the symbol y prime. Plus the second y times the derivative of x, which is still just 1. Okay, so you notice we're getting a y prime term and a non-y prime term that we're going to have to separate out because they're going to go to different parts of the equal sign. In the meantime, the derivative of e to the 3x is e to the u times du, the derivative of 3x, which is just 3, minus, now we're going to get e to the u, e to the x plus y, times the derivative of x plus y, and the derivative of x is going to be, and the derivative of y is going to be, so again, you're seeing you get a y prime term and a non-y prime term. They're going to need to be separated out. So let's distribute here. The e to the xy times xy prime, xy prime e to the xy, good, plus, good, equals, not much we can do with e to the 3x yet. Now we're going to distribute the negative e to the x plus y over here, so we're going to get negative e to the x plus y minus, good, y prime e to the x plus y. So now we have y prime terms and non-y prime terms. Let's bring all the y prime to the left, because this one's positive. So we have x, y prime e to the xy. And this minus y prime e to the x plus y here, we'll add it to the left side. So that's going to be plus y prime e to the x plus y. On the other side, on the right side, we still have this 3e to the x, the minus e to the x plus y, and we're going to move that y e to the xy to the 3x. Thank you, yes. Drop that along the way. That will not go well. Minus y e to the xy. Does that look okay? And finally, here now we factor out the y prime, leaving this x e to the xy plus e to the x plus y. Still have the 3e to the, I keep trying to make that 3x into an x, but it's not, and then minus y e to the xy. And then we divide all that mess to the other side, giving us 3e to the x minus e to the x plus y minus y e to the xy all over.
It should be 3 to the e 3x, right?
Thank you. And then x e to the xy plus e to the x plus y. Does that look right? Did I not pop anything else? Okay. And we could do second derivative, not on this one, that would be awful. And we can still evaluate at a point and get tangent lines. We can still evaluate the second derivative and get information about concavity.
So for this one, could we have taken what's it called, to get rid of the e, like not,
Natural log?
yeah, the natural log, not to solve it, but just to solve any e to it?
No, well, the problem is you can't distribute a natural logarithm. So it's not like you could take the natural log of this, natural log of this, natural log of this. You take natural log of both sides of the equal sign, But then what you got here with this subtraction, there's no good rule for, but remember, the rules for logarithms work well with a multiplication, but there is no property of logarithms that does anything with an addition or subtraction. And so this natural log of the right side is not really going to go anywhere. And so the y that we have stuck in here, there's not a good way to try to pull that out. So, okay, you bet. So that is that. Let's talk about derivatives of inverse trig functions. Derivatives. So this is now 3 point something else. Yeah, we're moving along here. 3.8, I think. Yep. 3.8. Derivatives of inverse trig functions. So I have gone through this in great detail on the supplemental videos. If this isn't very clear, I'm going to do one that I'll work through in detail here, and you can duplicate that for the others. It does get a little dicey with the derivative of inverse secant and inverse cosecant, why the absolute value goes where it does. There's an explanation for that, but if we're interested in finding, say, the derivative of the inverse sine of x, and remember, you'll see it written that way. You will also see it written as arc sine of x. So this inverse sine and arc sine are the same thing, just different names for that. So the idea is if we have, say, y is equal to the arc sine of x, we can take the sine of both sides to get rid of that arc sine for a moment. So that makes the sine of y the sine of arc sine of x. Remember, this is now taking like f of f inverse of x is what's happening here on the right side. So these are inverses of each other. They're going to cancel each other out and get us to x. You with me? So now we're looking at sine of y equals x. Now we're going to do implicit differentiation, which is why this comes after our discussion, our brief discussion on implicit differentiation. So this is a function y inside another function sine. So now when we differentiate here, we're going to get the derivative of sine, which is cosine, leave the inside function alone, times the derivative of y prime. Remember, our y prime is going to be that derivative of the arc sine. This is what we're trying to find. On the other side, the derivative of x is just 1. So we get that our derivative, our y prime, which is the derivative we're trying to figure out, is 1 over cosine of y. So now what we mean is, well, what does this mean? Well, let's go back to our understanding of right triangle trig. Remember, what an arc sine is, the arc sine of x, is the angle whose sine is x. The arc sine of x is the angle whose sine is x. So the angle whose sine is x means opposite over hypotenuse must be x. And then with a little, you okay so far? So now the Pythagorean Theorem, if I call this for a moment, say b, we have b squared plus x squared equals 1 squared. B squared is 1 minus x squared. B is the square root of 1 minus x squared. This is the square root of 1 minus x squared. So what we're getting here for the derivative of the arc sine is 1 over the cosine of this angle, this cosine of arc sine of x. So remember, this is saying take the cosine of arc sine of x, the angle whose sine is x. The cosine of this angle is adjacent over hypotenuse. That's just the square root of 1 minus x squared. So we're saying the derivative is 1 over the square root of 1 minus x squared. It's always really surprising when you first see it because you got all this sine, cosine stuff, but this is very algebraic. All you see is these x's in there. So that's the reason, that's where it comes from. Now, we have seen from what we have done before that we know if we know one derivative of something to do with trig, then we know that the derivative of the similar function is going to be the negative square root 1 over the square root of 1 minus x squared. That's what that is. This is 1 over the square root of 1 minus x squared. So it's worth noting that, you know, this radical, a radical is non-negative. So this is never going to be negative, this denominator. The numerator is always positive. So we're saying the derivative of an inverse sine is always positive. Derivative of an inverse cosine is always negative. Do you remember the others?
It's a little fuzzy.
So the derivative of an arctangent, this is the one that doesn't have a radical in it. This can be 1 over just 1 plus x squared. And you can derive it the same way that we did this, using implicit differentiation. And then the derivative, and we need to know these from memory. So the derivative of our cotangent of x would then be negative 1.
How long are you just redrawing one of the tests?
Pardon me?
You don't want me redrawing them?
Oh, no. You don't have time for that. You don't have time for that. No. These have to be memorized. Yeah. You don't have time for that. And this is the one that's kind of crazy. The derivative, and I'm going to write it as arcsecant, but you will see it written both ways, with the inverse function notation as well as with the arc notation. So this is going to be, does anybody remember? Here's where the absolute value comes in. And this is not the same order that we have there. It's the x squared minus 1 in the radical. So what's happening is, when you graph an arc secant, which is no easy task in itself, even on your calculator, then it's always increasing. And so its derivative has to always be positive, and that's why the absolute value gets inserted in there. By the same token, an arc cosecant is always decreasing, and so it must always be negative. So to guarantee that it's always negative, we make it a negative, and then put the x in absolute value so it doesn't goof up the negativeness of it. And so that is going to be our derivative of our cosecant of x. Okay? And then we can do these with chain rule too, where we replace the x's by u's, where that could be any function, and then what we get up here is a du, the derivative of whatever that inside function is. That's a very, very brief example. Let's do an example anyway. So let's say we have f of x is equal to, say, I'll say the inverse sine of 5x. So we're going to have to do a little chain rule action here as well. So f prime of x, I'm going to give you a moment, see what you can do with it. And there'll be some, I don't think any simplification much on this one. We agree? Okay, so it's du over square root of 1 minus u squared. Now, we also have the derivative of an inverse. So, of an inverse function in general. And this is, I think, one of the trickier things about in calculus here, and you don't use it very much. But remember, here we're talking about how do you find the derivative of f inverse of x. So the notation here is awful. This is how this is generally written. You write f inverse in parentheses, and then the tick mark outside the parentheses to indicate the derivative of that function. And a lot of times, because the notation is so awkward, what we'll just do is say, well, let's rename the inverse and call it g. Then, because we know that what makes an inverse is that f of f inverse of x must be x, right? That's what it means for two functions to be inverses, they undo each other. Then we can say that f of g of x is equal to x, where g is now what we have renamed the inverse function because of the awkward notation. Is that okay? So now we can take the derivative. Remember, we're looking for this is what we want, is how we're going to find the derivative of the inverse, which means we're looking for g prime of x. That's what's representing the derivative of our inverse. But this is our chain rule derivative. So we're going to get the derivative of the outside function, leave that inside function alone, times the derivative of the inside function. That's what we're trying to find, is that g prime of x, and the derivative of x is just 1. You with me that? So in solving for that g prime of x, we divide all this other stuff to the other side, and so our formula, if you will, is g prime of x, the derivative of our inverse, is 1 over f prime of g of x. I wouldn't try to memorize it. I don't try to memorize this, but I remember where it comes from and recreate it. I think that's longer lasting. Now, in general, finding this g inverse, evaluating the inverse, is what is tricky. Okay, that can be a challenge. And oftentimes, if it's done through an equation, you're going to need a graphing calculator to find it. Because you're going to have to say, if we're evaluating this at, say, 5, so if we wanted the derivative of the inverse at 5, we're going to have to set 5 equal to whatever our function is. Subtract that over, find the 0, and get that number to put in there. And I know it's very, very brief, and it shouldn't be, but I'm out of time. You can check out the video if you need some help on these, because this stuff is tricky stuff. So give it a shot.